So a single massive AI training run can consume enough electricity to power a small town for a month.
Yeah, it's a staggering amount of power.
Right, and we see the doom and gloom headlines constantly. The sheer scale of the energy being devoured by our digital lives is just mind-boggling.
It really is. I mean, you don't see it when you're just typing on your computer.
Exactly. You hit enter on a query, the screen thinks for a second, and you get your answer. There's no visible exhaust pipe on your web browser.
No, but there is a massive physical footprint.
But behind that seemingly weightless transaction is a distinctly physical, incredibly heavy, and incredibly hot reality. And so today, we're looking at the thermostat for the AI revolution.
That's a great way to put it.
For you, the listener, who wants to get past those headlines and understand the actual mechanics of the world, our mission today is to look at the solution. We are unpacking a source document for something called the PowerAsset Orchestrator, or PAO.
PAO, right.
This is a next-generation energy management platform designed by Supermicro and Bentaus. And it's basically attempting to stop the internet from literally melting the power grid.
Yeah, and the transition happening right now in this space is profound. I mean, the core challenge is balancing this insatiable demand for compute power with the harsh physical limits of our electrical grids.
And thermodynamics, too, right?
Oh, absolutely. What makes this PAO datasheet so compelling is that we aren't just looking at a software update for a server. We're looking at a literal bridge between the digital world of processing logic and the physical world of high-voltage electricity.
It's wild to think about it like that.
It is. It's essentially an operating system for a power plant that just happens to do computing on the side.
Let's set the baseline for what this platform actually controls, because it's a lot. The datasheet outlines PAO as an orchestration layer for data centers that are both grid-connected and what it calls behind the meter. Now, grid-connected is pretty self-explanatory. You plug the massive building into the local utility, but operating behind the meter fundamentally changes the relationship a data center has with energy, doesn't it?
It changes everything. We are talking about moving away from relying entirely on a municipal substation and instead managing an on-site microgrid.
A microgrid.
Yeah, that shift from being a passive consumer to an active energy manager is the entire foundation of this technology.
So they aren't just taking whatever the power company gives them.
Exactly. When a facility operates behind the meter in this context, they possess their own power generation and energy storage assets located physically on their own premises.
They're making and storing their own juice.
Right. They are actively participating in the generation, storage, and deployment of their own power. And the assets PAO is coordinating to do this are massive.
Yeah, based on the visual diagrams and the technical specs in the document, PAO is talking to the main power grid, obviously, but it is also communicating directly with battery energy storage systems.
And BASS.
BS. These are like industrial-scale chemical battery banks. And it's also orchestrating diesel or natural gas generators, right?
Right, the heavy-duty backup power.
And pulling telemetry from renewable sources like on-site solar arrays and wind turbines. I mean, the complexity of that ecosystem is wild.
It's incredibly complex.
You have solar panels that only generate power when the sun is hitting them at the right angle. Then you have wind turbines at the mercy of atmospheric pressure changes.
And the chemical batteries that can discharge instantly but take hours to safely recharge.
Yeah. Plus gas generators that provide reliable baseload power but actually consume physical fuel.
Add to that the main utility grid, which, provides a theoretically bottomless well of power, but is subject to intense, unpredictable price swings.
And regional instability, right? Like storms taking out lines.
Exactly. Managing all of that requires a system that doesn't just monitor things, but actually anticipates what's going to happen.
The way I'm picturing this system operating is kind of like a high-stakes algorithmic financial portfolio manager.
Oh, that's a really good analogy.
But instead of sitting on a trading floor moving billions of dollars between volatile tech stocks and stable government bonds to eke out a fraction of a percent, PAO is doing that with electricity.
Right. It's constantly, second by second, shuffling massive electrical loads.
It's evaluating the main grid, looking at the charge level of its battery banks, checking the fuel levels of the gas generators, all of it.
And trying to find the absolute best price for power while ensuring the servers never, ever drop offline.
So the currency it trades in is stability and efficiency.
Yes. But any portfolio manager, whether they are trading stocks or megawatts, they need perfect, instantaneous information to make a profitable trade.
Right. You can't trade if you don't know the price.
Exactly. They need to know the exact cost of their primary asset at any given millisecond.
Which opens up a huge logistical question. How does software actually know what a kilowatt hour of electricity costs at, say, 2 p.m. on a Tuesday versus 2 a.m. on a Sunday?
It's a great question.
Because the datasheet highlights a specific mechanism for this called price response via real-time locational marginal pricing, or LMP.
LMP, yes.
It indicates that the system directly integrates real-time energy market prices into its operations to identify price spikes or low-cost windows.
The concept of locational marginal pricing is vital to understand if you really want to grasp the economics of modern computing.
Right, because most consumers just think of electricity as a flat rate.
Yeah, you pay a set amount per kilowatt hour regardless of whether you are running your dryer during a blizzard or a heat wave.
Your bill doesn't change based on the weather outside.
Right, but massive industrial consumers like data centers, they operate on wholesale electricity markets.
Oh, okay.
And in those wholesale markets, the price of power is highly dynamic. It fluctuates based on real-time supply and demand on the regional grid.
So if a massive heat wave hits Texas, for example, and millions of air conditioners all kick on at the exact same time, the supply of available electricity shrinks while demand skyrockets.
Exactly. And the grid operators have to start turning on what are called peaker plants.
Peaker plants.
Yeah, these are usually older, less efficient, and much more expensive natural gas or coal plants that literally just sit dormant until demand peaks.
Oh, wow. So they only turn them on when things are desperate.
Right. And because it costs so much more to generate that marginal megawatt of power from a peaker plant, the wholesale price of electricity for that specific location on the grid just skyrockets.
And that is locational marginal pricing.
Yes, it is specific to the physical node on the grid, and it reflects the cost to produce 1 additional megawatt of power at that exact moment.
The source material provides a concrete example of this in action, actually.
Yeah.
The PAO AI agent dashboard shows real data being pulled into the system.
Oh, right, the dashboard numbers.
Yeah, it displays a current LMP of $44.2 per megawatt hour. But more importantly, it identifies a historical time spike.
What was the spike?
It logs that the highest LMP time period recently was, and I'm reading the timestamp here, 2025-07-28-00-00.35000.
So it's tracking it down to the minute?
Down to the second, really.
Mm-hmm.
The system isn't just reacting to the current price. It is building a historical model of market rhythms.
Right, to predict when the grid is going to get expensive.
Mm-hmm.
And the economic implications of this for a data center are staggering.
I bet.
I mean, without a system like PAO, a facility just blindly pulls from the grid.
Right.
So if that LMP at their local node surges from $40 a megawatt hour to $4,000 during extreme grid stress, which absolutely happens during severe weather events, the data center simply absorbs a catastrophic operational cost.
Just a massive bill for the duration of that spike.
Exactly. But armed with PAO, the facility has leverage. The software spots the LMP climbing. It evaluates its portfolio of behind-the-meter assets and executes a trade.
It commands the facility to drastically reduce its draw from the main utility grid, right?
Right. And seamlessly, in a fraction of a second, it signals the battery energy storage system to start discharging.
Or it spins up the on-site natural gas generators to cover the spread.
Yes. It rides out the grid's price spike using its own assets. And then when the wholesale price drops back down to that comfortable $44.2, it switches back to the grid.
And uses that cheap power to recharge the batteries again.
Exactly. It's brilliant.
But wait, if you're running a SaaS startup, right?
Hmm?
And you have purchased dedicated compute time in one of these server racks, you have a massive stake in this.
Oh, absolutely.
Because your biggest fear is that this so-called smart system is going to throttle your GPU mid-training just because natural gas prices spiked in the region.
That is a very valid fear.
Like, if I am paying a premium for AI processing, I cannot have my critical workload slowed down or dropped because the facility software decided power was a little too pricey that afternoon.
No, and the tension between facility economics and client performance guarantees is actually the central conflict of data center management.
How does PAO handle that?
The datasheet addresses this directly through its Service Level Agreement, or SLA, compliance feature.
The SLA compliance.
Right. The orchestration is entirely bound by contractual limits.
The SLA being the ironclad legal contract, guaranteeing, what, 99.99% uptime and specific processing speeds?
Yes, exactly. The system utilizes deterministic scheduling algorithms that balance energy costs without ever violating those contractual guarantees.
So it won't just shut you down to save a buck.
No, the software constantly calculates a highly specific threshold. It knows precisely how much power it can shed or which non-critical background processes it can pause without crossing the line into an SLA violation for a primary client like your hypothetical sauce startup.
Okay, so it squeezes every possible drop of margin out of the energy costs, but the client's workload remains fully protected.
Exactly, protected by the mathematical guardrails of the SLA rules engine.
It's walking a microscopic tightrope of efficiency.
It really is.
And speaking of measuring efficiency, the dashboard data in the source provides another crucial metric. It shows a real-time PUE of 1.34.
Ah, PUE.
Yeah, for you listening who are trying to understand the physical footprint of these facilities, power usage effectiveness is the industry's ultimate scorecard.
It really is the gold standard metric. PUE is a brutally simple ratio that reveals the thermodynamic efficiency of a building.
How do you calculate it?
You take the total amount of energy entering the data center facility, so that's every single watt drawn by the lights, the security cameras, the massive chiller plants, and the servers, and you divide it by the amount of energy used strictly by the IT equipment itself.
Okay, so meaning, if a data center draws 100 megawatts from the grid, and only 50 megawatts actually make it into the computer processors to do the math, the PUE is 2.0.
Yes. And a PUE of 2.0 indicates that for every watt of power used to compute data, you are burning another full watt on overhead.
This sounds incredibly wasteful.
Well, the vast majority of that overhead is cooling. It requires a staggering amount of energy to run the refrigeration cycles, the water pumps, and the massive fans needed to prevent high-density server racks from melting themselves into slag.
Literally melting.
Literally. A physically impossible, perfectly efficient facility would have a PUE of 1.0, meaning zero power is lost to cooling or power conversion inefficiencies.
So seeing a real-time PUE of 1.34 on the PAO dashboard means that for every watt going to the processors, the facility is only spending 0.34 watts on cooling and infrastructure overhead.
Which is quite good for high-density AI.
And the datasheet stresses that having this insight continuously, rather than just as a static monthly report, allows PAO to micro-adjust cooling systems in real time.
That real-time aspect is crucial.
But there is a gap here for me. We've established how PAO manages the macroeconomics of the grid and tracks the overall cooling overhead. But to actually change the PUE, the system has to interact with the things generating the heat in the first place, right?
Yes, exactly.
So how does this high-level portfolio manager interface with the thirsty silicon inside the server racks?
This is where PAO leverages its integration with SuperCloud Composer and a feature called GPU FLX.
GPU FLX.
Yeah. The core function of GPU FLX is workload automation at the hardware level. It possesses the capability to dynamically scale computational workloads on NVIDIA, AMD, or Intel GPUs based on that real-time power availability we discussed earlier.
The source material provides a snapshot of the raw power we are talking about here, specifically from a B200 chassis setup.
The dashboard numbers there are really eye-opening.
They are. The numbers pulled from the dashboard are wild. It lists GPU 7 pulling 953 watts.
Nearly a kilowatt.
Yeah, a single graphics processing unit drawing nearly a kilowatt of power. GPU 0 is pulling 915 watts. The rest are hovering in the low 900s.
And they are pulling this power while running incredibly fast.
Right, running graphics clocks at 2,000 megahertz and memory clocks at 5,000 megahertz.
We have to translate those numbers into physical thermodynamics to really appreciate the engineering challenge here.
Okay, let's do it.
Think about a standard microwave oven in a residential kitchen.
Sure.
That draws roughly 1,000 watts.
So every single GPU in that chassis is radiating the heat of a microwave running on high.
Yes. And the dashboard explicitly notes there are 32 GPUs in this total configuration.
Oh my God.
Imagine 32 microwaves, all running on high power, continuously, 24 hours a day, packed into a metal cabinet the size of a standard refrigerator.
That is insane.
The thermal density is hostile to physical materials. This is why the PUE ratio is so incredibly difficult to manage in modern AI workloads.
Because you aren't just supplying electricity to a microchip.
No, you're fighting a constant battle to extract immense heat before the silicon degrades or catches fire.
Because if you don't remove the heat fast enough, the hardware executes a self-preservation protocol, doesn't it?
Exactly. It thermal throttles.
It purposefully slows its own processing speed down to generate less heat.
Which instantly impacts the client's SLA.
Right, they aren't getting the speed they paid for. This makes the GPU FLX feature's ability to enable seamless workload mobility across clusters absolutely critical.
Yes, workload mobility is key, because thermal conditions inside a high-density facility are never perfectly uniform.
What do you mean?
Well, the ambient air temperature at the top of a server rack is often different from the bottom. An air conditioning unit servicing a specific aisle might experience a 2% drop in efficiency.
Just minor variations.
Right, but if that 953-watt GPU happens to be sitting in a slightly warmer pocket of the rack, it is going to hit its thermal limit much faster than a GPU 2 racks over.
Ah, I see. So the concept of workload mobility is kind of like playing musical chairs, but with massively complex AI models.
That's a fun way to look at it, yeah.
If P80 detects that a specific rack is approaching a thermal limit, or if the electrical circuit feeding that aisle is nearing capacity, it doesn't force a shutdown.
No, shutting down is the last resort.
The software literally picks up the computational workload in mid-process and seamlessly migrates it over the network to a different cluster in a cooler section of the room.
And it does this entirely preserving the uptime guarantee.
Wait, if PAO is going to move a workload from rack A to rack B to save cooling costs, how does software, which is just codeware, know what the physical temperature of the room is?
That's the missing link, right?
Yeah, a motherboard can report its own internal chip temperature, but how does the orchestration layer feel the environment of the facility to make these macro decisions?
Well, the software has a massive blind spot without external physical telemetry. It needs a dedicated nervous system embedded throughout the facility.
And in the PAO architecture, that nervous system is provided by the Bentaus Edge V1.0 board.
Yes, the Bentaus Edge.
The datasheet details this board as an edge IoT controller designed for intelligent environmental monitoring. And the sensor array it utilizes is incredibly specific.
It's very comprehensive.
We aren't just talking about a digital thermometer here. It lists temperature, humidity, airflow measured in CFM, differential pressure, and a camera or vision port.
Examining why each of these specific sensors is deployed really reveals the brutal realities of facility management.
Well, temperature is the obvious metric, given our 32 microwave analogy.
Of course, but the pairing of temperature with humidity is where the physics get complicated.
I was wondering about that. Why does a supercomputer care about the humidity of the air in the room?
It cares a lot. If the environmental air becomes too dry, the risk of electrostatic discharge increases exponentially.
Oh, static shock.
Right. A minor static shock that you wouldn't even feel can instantly destroy a dense million-dollar GPU array.
Ouch.
But conversely, if the air becomes too humid and your massive chiller plants drop the temperature of that air below the local dew point, the moisture in the air will physically condense into water droplets.
Directly onto the exposed motherboard.
Directly onto the electronics, yeah.
That is a catastrophic failure scenario.
Yeah.
So the Bentaus Edge board streams humidity data back to PAO.
Continuously.
And if the system calculates that the dew point is shifting dangerously close to the ambient room temperature, it can autonomously command the cooling systems to raise the supply temperature.
Or activate dehumidification protocols to prevent condensation from ever forming.
It creates a closed autonomous feedback loop based on atmospheric physics.
Yes. And the airflow sensor, measuring cubic feet per minute, serves a similar validation purpose.
Because you can expend massive amounts of energy chilling air, but if that dense cold air isn't physically flowing through the restrictive chassis of the servers to carry the heat away, the energy is wasted.
Exactly. The CFM sensor validates that volumetric flow is actually occurring. You need to know the air is moving.
The sensor that highlights the granularity of this system the most, for me at least, is differential pressure.
Ah, yes.
The text includes a very brief parenthetical note beside it that says, filter maintenance. Measuring air pressure to figure out when to change a filter is a fascinating application of physics.
It is. These data centers rely on massive industrial fans to pull air from the cold aisles, force it through the densely packed servers, and exhaust it into the hot aisles.
It's a lot of moving air.
And because that air must be free of particulates that could coat the electronics and insulate them, it passes through heavy-duty air filters. As those filters operate, they naturally accumulate dust.
Right, but in a residential HVAC system, you just swap the filter every few months based on the calendar.
You can't do that in an AI data center. A filter that becomes clogged faster than expected results in an immediate reduction in volumetric airflow,
Which instantly triggers thermal throttling on the GPUs.
which violates the SLA. The facility cannot rely on a calendar. It needs empirical data.
So a differential pressure sensor solves this by measuring the physical air pressure immediately in front of the filter and immediately behind it.
Exactly. When a brand new filter is installed, the air passes through easily, so the pressure on the front side and the back side are relatively equal.
But as the porous membrane of the filter clogs with dust, it acts as a physical barrier.
The fans keep pushing, causing the air pressure on the front side to rise, while the restricted airflow causes the pressure on the back side to drop.
And the Bentaus edge board calculates the growing difference between those two numbers, the pressure drop.
Yes. When that pressure drop reaches a mathematically defined threshold, PAO flags it.
This shifts facility maintenance from being a reactive scramble, where alarms are blaring because a server is actively overheating, to a proactive schedule.
It's totally proactive.
The system identifies that a specific filter on rack 12 is operating at 80% restriction, say, and generates a work order for a technician to replace it before it ever impacts the thermal performance of the GPUs.
It's a brilliant way to weaponize physics for predictive maintenance.
It really is. But looking at the final item on the Bentaus Edge sensor list presents a bit of a contradiction to me.
Oh, how so?
Well, we have highly sophisticated digital sensors calculating dew points and measuring microscopic pressure differentials. Yet, the final input is a camera or vision port for security and visual diagnostics.
That camera, right.
Why does a system capable of orchestrating multi-megawatt microgrids need a literal analog camera pointed at the server racks?
Well, digital telemetry provides an incredibly precise picture of what is failing, but it often lacks the context to explain why.
Give me an example.
So if that differential pressure sensor registers a sudden, total loss of airflow, the digital dashboard simply reports an airflow failure. The software doesn't know if a massive fan motor burned out or if the digital sensor itself just glitched. Okay. The camera acts as the physical ground truth for an operator who might be managing the facility from a control room 3 states away.
Exactly. The technician pulls up the visual diagnostic feed and instantly sees the context. Perhaps a physical fan blade shattered, sending debris into the intake.
That would be bad.
Or, in a scenario that happens more often than anyone likes to admit, perhaps a junior technician was performing routine maintenance and simply forgot to close the physical containment doors on the cold aisle.
Oh man, allowing all the chilled air to vent uselessly into the ceiling.
Right. The visual feed eliminates the human error variable in troubleshooting. And as the datasheet points out, it also secures the perimeter.
Oh, security, of course.
These behind-the-meter facilities, especially smaller edge locations integrating with local microgrids, are often largely uncrewed.
So tying a visual feed directly into the power management dashboard ensures that if there is physical tampering or a security breach, the orchestration system logs the visual evidence at the exact millisecond the power anomalies register.
It's all about context and verification. Okay, so we have thousands of data points streaming in every second. The macro grid pricing from the utility, the charge levels of the chemical batteries, the wattage of individual GPUs, and the differential pressure across hundreds of air filters.
It's a massive amount of data.
A human operator would drown attempting to correlate this data manually. How does a facility manager actually synthesize this fire hose of telemetry to make decisions?
The synthesis layer, what we might call the brain of the PAO platform, is handled by the SuperCloud Composer AI agent.
The AI agent?
Yeah, the datasheet details this as a large language model, an LLM, that can be deployed on-premise or in the cloud. It leverages LLM-driven business rules to dynamically interact with all of the systems we've discussed.
The source material actually includes a mock-up of the prompt interface to demonstrate how radically this changes the user experience.
It's a huge shift.
Instead of navigating a labyrinth of menus, the operator types a natural language prompt. It says, give me a recap of all current metrics at our site: PUE, LMP, average CPU wattage, total GPUs, and when the highest LMP time period has been in the last 7 days.
Just a normal conversational question.
And their AI agent parses that sentence and returns a cleanly formatted response. PUE 1.34, LMP 44.2, 915.0W average GPU, 32 GPUs total, and the exact timestamp of the grid price spike.
The paradigm shift in user interface design here cannot be overstated.
Because traditionally, obtaining that specific cross-section of data would be a nightmare, right?
Oh, absolutely. It would require a human operator to log into 3 separate proprietary software dashboards. They would have to export the data logs, manually align the timestamps, and run the calculations themselves.
And by the time the human completes the analysis, the locational marginal price on the grid has already fluctuated.
Exactly, rendering the data obsolete.
The datasheet notes that operators can issue commands the same way, typing things like reduce cooling by 5% or optimize BSS charge cycles. But this introduces a massive trust issue for me.
The hallucination problem.
Exactly. I use consumer LLMs every day, and sometimes they confidently hallucinate entirely fabricated information.
They do.
The idea of giving a language model autonomous control over industrial diesel generators and highly volatile battery systems seems incredibly reckless.
It's a very common concern.
How does an LLM, which is essentially just predicting the next word in a sequence, safely interface with physical hardware APIs without accidentally commanding the system to overload the main breakers?
The hesitation to hand physical infrastructure over to AI is the primary barrier to adoption in the enterprise space right now. But the mechanism that makes this safe is found in the datasheet's mention of business rules and SLA compliance.
Okay, break that down for me.
The LLM is not a completely open-ended intelligence directly wired to the diesel generators. It functions strictly as a translation layer.
So it interprets the human intent, but it doesn't have the final say on execution.
Right. When an operator types reduce cooling by 5%, the LLM parses the natural language and translates that intent into a highly structured data payload, like a JSON file or a specific API call.
But it doesn't send it yet.
No. Before that command is ever sent to the physical chiller plant, it must pass through a deterministic rules engine.
The guardrails.
Yes. This engine contains the hard-coded physical limits of the facility and the contractual requirements of the SLAs.
So the guardrails are algorithmic, not linguistic.
Precisely. If reducing the cooling by 5% would cause the ambient temperature in Rack 12 to exceed the physical operating limits of the GPUs, or cause a processing slowdown that violates the SLA, the rules engine simply rejects the API call generated by the LLM.
The AI can suggest and translate, but it's physically incapable of executing a command that violates the thermodynamics or the contracts governing the facility.
That's exactly right.
But if we have to put so many guardrails around the AI, why use autonomous systems at all? Why not just keep well-trained human operators in the loop for every major decision?
Because the transition to autonomous orchestration is not a luxury. It is a mathematical necessity dictated by the speed of the energy markets.
Because humans are too slow.
Human reflexes are completely incompatible with the latency of locational marginal pricing. If a price spike hits the local utility node due to a sudden drop in wind generation, for instance, that spike might only last for 4 minutes.
4 minutes is nothing.
Right. By the time a human operator registers the visual alarm on a dashboard, authenticates their credentials, navigates to the battery control menu, and manually executes the command to transfer the facility's load to the BAS, the price spike has passed.
And the facility has already absorbed thousands of dollars in excess energy costs.
Exactly. The autonomous agent is the only mechanism capable of reacting with the microsecond latency required to capture those economic windows.
It is high-frequency algorithmic trading, but instead of trading synthetic equities, it is trading physical electrons.
Yes. Beautifully said.
So if an enterprise facility manager understands this necessity and wants to implement the PAO platform, how does the deployment actually work? The datasheet outlines a 3-tiered licensing structure.
The licensing model is interesting because it reveals Supermicro and Bentaus' strategy for overcoming the exact trust issues we just discussed.
Right, because you can't just take their word for it.
The tiers consist of the main PAO software plugin for SuperCloud Composer, the Bentaus Edge hardware and software license for the on-premise telemetry sensors, and a highly specific trial license.
The trial license part number SFT PAO trial offers a free 30-day trial for up to 200 nodes.
200 nodes is huge.
In the context of a SuperCloud Composer environment, a node represents a managed endpoint, which typically equates to an entire server or a dense compute unit within a rack.
Right. Providing a trial that scales up to 200 nodes is a massive allocation of resources. A 200-node footprint represents a multi-million-dollar physical deployment and a massive amount of computational power.
They aren't just giving you a lockdown demo video or a simulated software environment. They're offering a massive physical sandbox.
The strategy is entirely focused on proving empirical trust. You do not convince a risk-averse facility manager to hand over the orchestration of a 50-megawatt SLA-bound data center with a sales pitch.
Obviously not.
The 200-node trial allows enterprise architects to deploy the AI orchestration in a confined, heavily monitored segment of their actual infrastructure.
So they can see it work with their own eyes.
Yes. They can empirically observe the system managing the thermal limits of the GPUs, reacting to real-time grid pricing, and navigating the deterministic rules engine to protect the SLA, all without exposing the entire facility to operational risk.
It allows the deployment to meet the architecture where it currently exists, as the datasheet emphasizes options for on-premises, hybrid, or cloud deployments.
It's very flexible.
This isn't just for building new state-of-the-art facilities. It's designed to retrofit intelligence into the massive footprint of legacy data centers already straining the grid.
Which is where the biggest impact will be felt, honestly.
To bring all of these concepts together, we began by looking at the macroeconomics of wholesale energy markets and locational marginal pricing.
The high-level stuff.
Right. Then we zoomed in to examine the terrifying 953-watt thermal output of a single GPU and explored how measuring the microscopic air pressure drop across a physical filter prevents catastrophic thermal throttling.
The physical realities.
And finally, we unpacked how all of this disparate physical data is translated by an LLM and filtered through a deterministic rules engine to autonomously manage the facility at a speed human operators simply cannot match.
It represents a closed-loop architectural philosophy, seamlessly binding the digital intent of computational workloads with the unforgiving physical realities of thermodynamics and grid infrastructure.
For you listening, whether your company is buying AI compute time, if you are analyzing the fragility of regional power grids, or if you simply want to understand the physical cost of the digital tools you use every single day, the PowerAsset Orchestrator offers a window into the future of infrastructure.
It really does.
It is the mechanism the industry is building to ensure our digital expansion doesn't physically break the world powering it.
And the conversation constantly revolves around how this technology protects the data center from the volatility of the grid. But consider the inverse implication.
What do you mean?
If platforms capable of this level of autonomous orchestration become the ubiquitous industry standard, we will have thousands of massive facilities globally, all utilizing AI to instantly buy power when there's a surplus, store it in massive chemical batteries, and shed loads or discharge power back during peak demand.
Oh, wow. I never thought about it like that.
The data center ceases to be a parasitic burden on the local utility. It functionally transforms into a highly intelligent, distributed battery.
It becomes part of the solution.
Exactly, potentially becoming the primary stabilizing force for the entire global energy grid.
That is a staggering paradigm shift to consider. The infrastructure causing the power crisis might hold the architectural key to solving it. Keep looking past the interfaces and diving deep into the systems that run the world. We'll see you next time.